Hey everyone, Mr. Fransky here. I just wanted to do a couple problems from the sinusoid packet. I think I'm going to do 3 of them, and hopefully that kind of gets you jump started for how to do these. I like these problems a lot. They're kind of like puzzles. They give you a little bit of information. You have to find the equation. I think they're pretty cool. So let's give it a shot. Alright, so we have a tsunami here, first of all. A fast-moving ocean wave caused by an underwater earthquake. The water first goes down from its normal level, then it rises an equal distance up above its normal level, and finally returns to its normal level. That sounds sinusoidal. Suppose a tsunami with an amplitude of 10 meters approaches the pier at Honolulu, where the normal depth of the water is 9 meters. The period is about 15 minutes. Okay. So first they want us to sketch the graph. So it starts at 9 meters and it says it first goes down from its normal level, then rises the same distance. So we start at 9 meters. Let's say 9 is like right here. Okay, so we start at 9 meters. It goes down and the amplitude is 10. So it's going to go down to -1. And then it rises the same height above. So let's say that's up here. So that's going to be at 19. So sorry, down to a -1, back to 9, up to 19. And then back down to 9. Okay, so down, up, and then returns to its normal level. Perfect. All right, they tell us the period is 15 minutes. So this is going to be 15 minutes right here. That means that right here is half of 15. That's 7.5. All right, now I might have to grab a calculator for this, but what's half of 7.5? Was that 3.75? And then right here we'll be at, so it's like 10, 12.25, I think. He asked with a question mark. I think that's right. Then, let's see. Nope. 11.25. There we go. Because then plus 3.75 more, yes, would be 15. Okay, so now we can kind of draw in our graph. So it starts going down like that. We come up through here. So it kind of looks like a sine wave. All right, so our center line is at 9. Okay. Oh, too far. Okay, so then I want an equation for the graph. So lots of things we have to write down here. So period is 15. And let's see here. I'm getting ahead of myself. So remember, we always have 4 choices for graphs here. So we could be dealing with positive sign. Sign looks like this. We could be dealing with negative sign. That's just flipped over. Looks like that. We could be dealing with cosine, which looks like this. Or it could be dealing with negative cosine, which looks like this. So I always kind of like to look at the graph and say, which one would make the most sense? I could use any one of these, right? If I use cosine, I'd be shifted by 11.25, right? If I use positive sine, I'd be shifted by 7.5. It looks like the easiest one to use here is going to be negative sine, because that one wouldn't be shifted at all. So negative sine is kind of my winner, because that's just going to go down right away from the center line. So I'm going to be using negative sine here. So my goal here is to have negative a sine bx minus h plus k. Okay, so I need to find h, k, b, and a. That's basically what I have to do. Okay, so the first thing I know is the period. Period is 15 minutes, and that's always equal to 2 pi over b. Okay, so you can solve for b by swapping the 15 and the b. So b is equal to 2 pi over 15. So we got that right away. So that's this 2 pi over b thing. That's one thing you just have to know. Sorry, my slides are jumping all over the place. So the 2 pi over b, that's just one thing you have to know. Swap the 15 and the b, we got that. Okay, a is the amplitude. And the amplitude, my goodness gracious, they tell us what the amplitude is. Okay, amplitude is the center to the top, and that is 10. So a is 10. That is going to get really annoying. Sorry, guys. Okay, so the amplitude is 10. And then what else do they tell us? Let's see, we're shifted 0, so h is nothing. Right, because we're right on that. Has to stop. Because we're right on where negative sign would start. And then, let's see, what's the last? K. So k, we are shifted up 9 units. So k is 9. All right. I don't like that at all. Okay. All right, so now we can put everything together. So we have negative. A is 10. Sine of b is 2 pi over 15 times x, no h at all, so don't have to worry about that, and then plus 9. And that's the easiest way to do it. You could do this with any of the other functions. So like if we want to use positive sine, all that would happen is the x in here. So, oh my goodness. Okay, so if you had positive sign, it'd be positive 10 sign. This would be x then minus 7.5. Okay, because that 7.5 is going to shift you that far to the right. Okay, so some differences depending on which function you choose to use. We'll see that kind of in some of the later examples. Okay. All right, so there's our equation. Now we actually do want to move forward. Hopefully it'll stay on this slide. Okay, so after the tsunami first reaches the pier, predicted the depth of the water 4 minutes later. So what we're going to do for that, just plug 4 right in here to your equation. Okay, so to do that, I grab a calculator. I do 4 times 2 pi, so 8 pi over 15. Take the sign of that value, multiply by negative 10, add 9 to it. And that's going to tell you, so at 4 minutes, we should be somewhere right about here. So it's probably going to be actually pretty close to 0. Right? So the depth of the water is probably pretty close to 0 at 4 minutes. But all you do is plug the 4 in, and you can check online to get that. I don't have a calculator ready to go here. So, but you just plug in the number here. Make sure you're in radian mode. On those scientific calculators, there's a button called DRG. That stands for degree radian gradient. And just make sure that it says RAD at the bottom of your screen on those scientific calculators. That's going to be radian mode. Because you always want to be in radian mode for these if you're using the 2 pi over b. All right. So, I'm going to put a question mark there. You guys can do that on your own. Just plug 4 into your equation. According to your model, what would the minimum depth of the water be? That would be negative 1 meter. So what does that mean in terms of the context of the problem in the real world? Because it can't really have a negative water depth, right? So the way I think about this, right? So the ocean kind of has a slope like this, right? The sand kind of drops into the water. So here's your water. So when it slides down, I kind of think about this like, whenever I took baths, my parents hated it because it was like a science experiment more than me taking a bath. But if you've ever been in a bathtub, and you like, so you're sitting down in the bathtub, here you are, okay, these are your knees. So if you ever like scoot forward and backward, you notice how you can make waves. You know, if you like get them really going, you can kind of swash all of the water back like this. You can see the bottom of the bathtub. That's kind of how I imagine this. Like the entire ocean is swooshing back this way. You can see, so at that point it'd be like back here. You can see all of this land. So that's like the negative depth. It's like the ocean has sunk below, even lower than the depth, and the whole thing rushes forward. And that's when all the water rushes forward in the bathtub and splashes out all over the place, and your parents get really upset with you. Yeah, that was me. This is Mr. Fransky, like, as, I don't know, 8-year-old. Okay? Well, 5 years old. I don't know, something like that. Anyway. So that's kind of how I interpret this, is the water's all sloshing back, and then it's going to all rush forward, and that's when you end up with the water way higher than it should be, is when it all sloshes forward. Kind of cool. All right, so tsunami travels at 745 miles per hour, 745 miles in 1 hour. What is the distance that it travels in one period? All right, so we want to figure out how far this is in terms of miles, maybe, in one period, which is 15 minutes. So 1 hour is 60 minutes. And then it's 15 minutes to 1 period. So what I would do here is 745 times 15 divided by 60. All right, and again, I don't have my calculator on hand. 15 out of 60 is a quarter, so this is just 745 divided by 4. But that'll tell you how many miles it moves in 1 period, or in 15 minutes. And you'll find that these things move really fast and really far. 745 miles per hour, obviously very fast. It's close to the speed of, speed of sound is 763 feet per second. So I'm not sure how close this is to the speed of sound, but that's really fast. And that's one of the problems with tsunamis, is that after there's an earthquake, when I was living in Chile, we talked about this a lot, they had these, when there was a big earthquake in Chile in 2010, and there was a giant tsunami that came and wiped out a bunch of homes and people, and there was a lot of death, and so they kind of were like, how do we deal with this? And now whenever there's an earthquake, people get really nervous because the tsunami comes, could be 10, 15, 20 minutes or an hour after. So everyone's kind of on edge during that period. And so they have these really high ground tsunami meeting points. And so anytime there's an earthquake, everyone goes to kind of high ground to get away from it. But they move so fast and they're so unpredictable. That's why these are so dangerous. So anyway, a little bit of extra tsunami knowledge from Mr. Fransky. There you go. Looks like my slides aren't moving around, but I should probably knock on wood because we'll see if it happens again. All right, so next up, Ferris wheel. Ferris wheel is 50 feet in diameter, so the entire diameter is 50 feet. Okay, and makes 1 revolution every 40 seconds. So 1 revolution in 40 seconds. All right, the center of the wheel is 30 feet above the ground. Interesting. So the center of the wheel is at 30 feet above the ground. All right, and the diameter is 50, so from here to here is only 25. So that must mean that the minimum height of the wheel, the bottom here, must be 5 feet off the ground if the center of the wheel is at 30. So then the maximum height of the wheel would be 50 plus 5. That's 55 feet. Okay. All right, so the amplitude then, the amplitude would be the distance from the center to the top. So that would be 25. You go 25 up and 25 down, 25 up, 25 down, but the bottom of our graph will only be at 5. It won't go below because it's going to be the distance above the ground. So they ask lots of questions here. I'm actually going to start just by graphing this, and we'll kind of figure out all the rest of it. So our maximum height is going to be up here at 55. Our minimum height is going to be down here at 5. So now we can kind of figure out our vertical translation. So halfway between 5 and 55, add them together, divide by 2 is 30. That makes sense because that is the center of the wheel. Okay, so our vertical translation will be up 30. The period, they tell us it goes around once every 40 seconds. So b then, so remember the period is always equal to 2 pi over b. So we swap the 40 and the b. b is then equal to, let's see, 2 pi over 40, which is pi over 20. Okay, so phase shift depends on the equation, which is very true. And let's see, if you get on at the beginning, so if you get on, it says we get on at the bottom. So we start at the bottom, and then we'll go up, and then we'll come back down. And that entire thing should happen in 40 seconds. So I say the phase shift depends on the equation. So remember, we have 4 choices for the equation. We could use sine, could use negative sine, could use cosine, and we could use negative cosine. So it looks like the way that it's set up, negative cosine is probably our best option. But we could use whatever we want, right? This point is 20 seconds, this point is 10 seconds, and this point right here is 30 seconds. Excuse me. And this is 0, so we could use negative cosine with no shift. We could use positive sine with a shift of 10. We could use positive cosine with a shift of 20, because we would start at a maximum point then. Or we could use negative sine with a shift of 30. All those would be okay. All right, so let's see here. So I'm going to redraw the graph. That's a beautiful graph right there. Look at that. This is 30, this is 5, this is 55. 40, 20, 10, 30. Okay, so first they want one with the negative cosine function. They choose that because that is done with no phase shift at all. So stealing our values from before, so our amplitude from the center to the top is, looks like 25. So we have 25 negative, because negative cosine. And then our b, I believe, was pi over 20. So then x, no shift at all, because it starts at a low point and goes up. So we have no phase shift. It's just been moved up. And then plus 30. So positive cosine function. For that, we need to start at a maximum point heading down. So that's going to be a shift to the right of 20, right? Because normally that would start up here and head downwards, but it's been shifted to the right by 20. Takes a little bit of practice to get this, but eventually you figure it out. So 25 cosine pi over 20 times x minus 20 plus 30. So how about the positive sine function? Positive sine function should start at a middle point and go upwards, normally. So to do that, we have to be at 20 here, or 10, excuse me. That starts at 10 and goes upwards. So that would be a shift to the right by 10. So we 25 sine pi over 20 times x minus 10 plus 30. So you should be able to do all 4 of these for every sinusoid graph. You should be able to do positive, negative of both sine and cosine for every sinusoid graph like this. Negative sine function, so negative 25 sine. So let's see where negative sine would start. Negative sine would have to start at a midline going down. So it looks like that would be a shift of 30. So pi over 20 times x minus 30 plus 30. Now at that point, you could go backwards, right? You could say, well, negative sine could happen at negative 10. Right? So this would be the same as shifting by positive 10, right? And that makes sense because all you're doing is changing by 1 full period, right? You can always change by 1 full period. This thing goes on forever. Oh my goodness. I swear. Go away. I don't care about notifications. Please go away. There we go. Okay. So if you change by a full period, right, this thing keeps going forever and ever and ever. Right? So this would be at 80. So you could add 40 to any of these, right? So this could be x minus 40. You could start at a bottom point if you shifted another 40 over. I guess that'd be here technically. Here would be 80. This guy you could change to 60 or 100, right? You can add or subtract a full period anytime because that's just going to move the entire graph one period and just put it right back on top of itself. It's no big deal. Okay, hopefully that made some sense. The reason I wanted to do this one was to show you can use all four. Let's take a look at Tarzan. Tarzan is one that seems to give people the most trouble, which is why I like to do it here. Come on. Oh, this is being so problematic. There we go. Okay, so Tarzan is swinging back and forth on his grapevine. There it is. As he swings, he goes back and forth across the riverbank, going alternatively over land and over water. So notice that his branch is kind of a little bit over the land. So he swings further back over the land, looks like 23 feet to the left, and then he only swings 17 feet over the water, because technically I guess maybe the riverbank should go a little further, but doesn't matter. Excuse me. So he swings back over the land, forward over the water, back and forth. Jane decides to mathematically model his motion. Of course, why not? So she starts her stopwatch. T is the number of seconds the stopwatch reads, and Y is the number of meters Tarzan is from the riverbank. So he goes forward over the water, then back over the riverbank, water, riverbank. So sinusoidally. So assume Y varies sinusoidally with T, and the Y is positive when Tarzan is over the water and negative when he is over the land. Okay, I buy that. Jane finds that when T equals 2, Tarzan is at one end of the swing where Y is at negative 23. So when we are at 2 seconds, he's at negative 23. This should really go a little lower, I think. So let's say negative 23 is like right here. So let's say 2 is there, so he's down here. When T equals 5, he's at the other end of the swing where Y equals 17. So let's put 5 like right here maybe. And he's up at 17. Right there. Okay, so plot those 2 points and sketch a full period. So he goes from bottom to top in that much time. And then I'll have to come back to the bottom. So there's one full period, bottom to bottom. So it took 3 seconds to get here, so it'll take another 3 to get here, so we'll be at 8. Okay, we have to figure out our center line. So let's see, halfway between 17 and negative 23. If you add them together, gives you negative 6 divided by 2 is negative 3. So negative 3, that must be where his vine is attached to the tree. So this must be at, I guess, 3 feet left of where the water's edge is. So negative 3 is our center line. So halfway in between 2 and 5 would be 1.5 in between, so it would be 3.5. And then here, I guess, would be 6.5. Yeah. Okay. So now I want us to write an equation. So we're going to have to figure some stuff out for that. Amplitude. Amplitude here is from the center to the top or center to the bottom. Looks like that's 20. The period, full period, looks like is 6 seconds. And that's equal to 2 pi over b. Swap the b and the 6. B, sorry, my b's and 6 kind of look the same, is going to be pi over 3. And then the vertical shift is looks like down 3. Oh my goodness. I think my calibration's off. I think that's the problem. Okay, so the vertical shift is down 3. And phase shift, I'm going to use negative cosine because we started at a low point. So I'm going to do right 3. Or right 2, excuse me. Alright, so I'm going to use negative cosine there. You could use also sine if you want to start here, cosine starting here, negative sine starting here. Okay, so what do we have here? So we have negative cosine, so we have negative 20 cosine because of our amplitude of our b value, pi over 3, times x minus 2, and then minus 3. There we go. Cool. Alright. Come on. Just change when I don't want to. There we go. Okay, so predict y when t equals 2.8. So for that one, all we're going to do is plug in 2.8. So I have negative 20 cosine of pi over, was it 3, I think? X minus, 2.8 minus 2. And then plus, minus 3 at the end. Okay, so grab your calculator, do 2.8 minus 2, that's 0.8. Multiply by pi, divide by 3, take the cosine of that answer. Remember, you can use second negative sign. to be able to get that answer from that you just used. Multiply by -20, minus subtract 3, and that'll give you the y value. I don't have a calculator handy, so I won't calculate that. I'll let you do that. Answers are online, though. Where was Tarzan when Jane started her stopwatch? For that, plug in 0. So pi over 3 times 0 minus 2. Cosine of that times -20 minus 3. That'll tell you where he was when she started. All right, I think that's the last one I have for you. So, sorry about all the slides moving around. Hopefully this was helpful for a jumping off point, and you're able to try some of these problems, and they aren't too bad. Love you guys. That's why I'm here. Have a great day.